Okay, clock. I have 40 minutes timer set. Set it to the 5 minutes time, so the 40 minutes time, so great. So I've set a 40 minutes timer. The time now is 4:54 p.m. I'm announcing I'm 30 years old now. Well, I'm actually 24 years old, but my mental age is 30, so I'm 30 years old, so literally. And 25th of March, 2026. The time now is 4 4:54 p.m. So let's get without further ado, let's get to it. So much to do. Today I'm trying to learn. Uh, I've got my. I'm trying to build three things: robots and drones. Let me decide. Let me think. I have to decide either robot or drone. Should I? Basically, I'm thinking what to do. So I've got my sheet of paper here, and I'm trying to model it properly. But it's not enough. So let me go and get the other piece of paper, sheet of paper. So I'll go here, set up sheet of paper. I'm gonna use it to work on this project. But it's all done. I'm trying to study calculus one, two, and three. I'm trying to learn rocket science today. So let me watch a video and watch. Let me just see if I can get some notes here. So I can't find my book, basically. My other book, my diary or my journal, but my other one. But I have to buy another one. That's what that means. So I can't find it. But I'm keeping record on the big computer. Ontological Bayesian intelligence for Muko OS, M for Mike, M for Mike, Q for Kilo, O for Oscar. We're building rockets and we're building rockets for drones, drone rocket, and we're gonna have drones. So let me just research what is already out there first. This is more of a research procedure. So what is an orbit? Here, should I switch to this Coursera here? Let me start with this video here. Let me start with this video here. I'm kind of getting old, but I'm getting old, yes. So let me go and flip this video here. Let me just go and change this to 163. So this video is watching, and this video is here. It's orbit types introduction. Let's watch introduction. So basically, these are used for models of the problem. See, I see the models first. So I do because the gravity of the height is different from the actual velocity. I noticed you're going with this video, but I'm listening to the video stuff. So So my next step is actually I'm really good at problem I'm gonna do, but I'm trying to have this system do something for me, and that thing is know when it's falling and know detect when it's falling. Basically, I have a model drift, and drift theorem basically is what the formula initial paper. Again, but we have a repository. So, this is basically one paper. Here's a structure of paper, but it does do the work. It does get the work. So, seriously, this is basically the drone model. You can also kind of payload horizontally with it. So you're gonna be drifting with the payload. But the payload is a drone. So I'm using rocket science to model the orbit of a system over the curvature. So you know over time. And it's not basically the altitude you get to the altitude that you get that you used to start gliding, so you don't have to put in a thrusters. So you don't have to turn on the boosters anymore. And if I can make that, if that is 15 meters, basically, I don't know what the altitude is, but that's another altitude. It's not 0 G. It's not that. It's not that. It's something else. So let's go to the video. So you have three types of orbits. You have uh, uh, let's see. Let me just write this out properly because I haven't got my ruler or anything, but I have to just make it believe what I'm doing. So calculus one, two, and three. Uh, but the trident is going to tripod system for drone delivered network. So it has to be done properly because I'm doing the code. I'm the one doing it. So I'm the one programming the drones to do it. But I'm putting my own firmware into the drones. But if I just write the code, I'd be much happier than just write the code. But I've never done manufacturing before. So, let me not start with let me just try to program the drones because I'm good at, I'm good at programming drones. And, if you're going to respect this code, it will be better than do that. So, the orbit types are elliptical orbit, and you have, you know, so basically, you get the elliptical orbit first. Oh, that's good, that's good. Okay, so this is all going over my head. I can't even write it down, so I'm trying to study this properly. Let me try and change the caption on. Let me see here again. I'll put the playback to 65. So you're gonna have. So let me try to. Okay, the difference between a satellite in orbit and a ball that's been dropped is the horizontal speed. I am trying to interpret this properly. You know, my systems know when they're moving, know when they're stopping, and know what they're doing. But if you don't know what they're doing, know where they are, how can they know? How can I account for the system? So basically, I've got my work here. Basically, just pin this down. Let me just start this in the favorite section. Start it here. Start it here. Let me just add this to start. Yeah. So basically, so put it in system computing. How many floors? How many letters? Actually, will be a dashboard. No. I'm trying to have my website up and running again. One second. This is a deviation. This is my physics measurement. So this is I'm doing A-level physics. Well, I'm trying to use orbits too. So let me get this straight. So it's the hard translate basically, and let me write it down. So I go to people. Let me write it down now. Let me write it down here. So I got my paper here. So this will be trouble if I don't write it down now. But let's see what I can do to make it better. Um, so basically, let me try a model this way. So I'm trying to define a system of I can't remember all my symbols anymore because I've got my book to remember my symbols. But alpha, beta, gamma, theta, gamma, delta, epsilon, eta, zeta, omega, theta. Yeah, that's remember. So that's remember. That's all that was I remember. But let me try and do this. So I'm thinking of this NSIGII drone system as taking a kind of cargo and taking a payload into space. But I don't know how to put it in a formal framework here. I know you have a little orbit and you're gonna have a little orbit. But when it comes down eventually, but yes, that's the stage. So I had that with stage. So it's not there. So let me just focus on getting up to above the surface of the Earth, 500 meters physics kind of physics model view of the so let's say we have two drones, they do organization, but they are two drones that are drifting um towards each other. So um let's say we have three drones. How many drones do we have? So I'm trying to now model how this will work computationally. So you have three drones, and three drones were flying to deliver aid to someone. So one delivers food, one does basically kind of a bird fly simulator. So one does to do with the food, one does the defending with kind of like a formation system using dimensional game theory and dimensional game theory, which are non-frozen, zero sum games, which are basically in the style. And the filmmaker has to develop a drone, food and shelter to someone that needs that's moving away because the world is naturally chaotic. So, you can understand that the fictional pain is a real reality where the drones are flying and they are going to be eventually shut down, but they're going to be computing ahead of time. So they're going to be, trying to compute something like, not compute something, like, what can come of zero observer, via system. So people don't know there's being a system is being watched. I can do this for myself. I don't want to draw a picture. Yeah, I have three pictures already. So this one I did here. So this is my first drawing. This is what I did before a long time ago. And this is a spring, and it's basically has some kg, and the drone is carrying some weight, and that drone can bring it up and down. So obviously, might have sprinkle this, but sprinkle this in the drone setting is, I haven't done takeoff. So let me try to do drone takeoff. Drone takeoff horizontally or vertically, because if you take it horizontally, you can start to gain some that'd be 45 degrees angle. So let me try to model that properly. Um, should I do drone rockets? One with a rocket. Uh, so let me try to do point man, wingman, and light gunner. Delivery drone. Mm. I'm still thinking about the concept of the model, but the problem is a lot of things gonna get weather, you're gonna get a lot of other things, other factors involved. But let's just work in the kind of the best case, just that the drone is not being attacked. I see it's been attacked before. Yes, I did say that, but let's work with this model. Let's work with this model here. I'm gonna model. So 5 kg or 5,000 kilograms of food. Let's say 5 kg. 100 kg is a bag of rice. 100 kg is a bag of rice. A bag of rice. Let's make it 200 kg, 250 kg. A bag of rice as a bag of rice. 250 kg is a bag of rice, and the drone has to go to spring to go up and down. So that means I have three note through the drone. So let me try and do it. Let's just finish the video, watching the video first. Let's finish the video so we can get to. I feel so embarrassed. See this Okay. So I've learned a lot from that, and I'm trying to do it properly now. So let me come back here. So, it doesn't, I don't hate it. I don't hate it, but I'm trying to follow along with the kind of framework I already know. I think I have to go to Calculus One. Calculus One can show me how to do this properly. But let me start write something down. So let me write some things down. So I'm gonna follow kind of a vertical orbit. So basically, you have to go up to go higher. So basically, if you have to go up, you have to do a loop, and it comes down. But that was basically the sparse missile I made, and that's basically for if you can put on a rocket, it'll go like but it doesn't need to go. This is not but if I have two drones, two guard drones and one drone, I can get myself food on shelter. You know, based on all the but I'm moving away. So let me try and formalize it in language, in the way I know it. So you're gonna have let me see my people. A rocket in orbit. I'm gonna think. A rocket in orbit stays in orbit uh, when the electrical when it's in when the horizontal 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 vector component horizontal minus the let me see because I think it's so let me just try to find the system. Obviously, let me think. I can't remember. So, a ball falling down and a rocket, and rocket in orbit is the difference is the horizontal velocity, horizontal velocity, and velocity is basically moving in a direction, and that movement is basically like an integral or derivative of space. The system has to be modeled in a way that is it's I'm thinking of one more taking off. I'm thinking of a drone. But if I have a do takeoff, my drone will basically fly straight up. It doesn't need to go straight up, but it needs to go straight up. It's a rocket. So let me try to do it because I'm trying to have a vertical takeoff. So let me try to write a few more specification for that. Should I? Okay, let me do it. So let me just start with pen to paper. So I'm gonna see here. Because as soon as I got my desk, my phone is still charging. A rocket. Oh, I can't see these guys. This is my charger. A rocket. In orbit stays in orbit because it has a different. A rocket. An object. Uh, a rocket R stays in orbit such that because the horizontal vertical a vertical takeoff protocol. Should I model the vertical? I'm not thinking too hard. I'm thinking too so. Let me start it. So in SIGI, in SIGI, vertical, vertical, uh, vertical, drift, take off, take off protocol. So what does this mean? So, the SIGI vertical takeoff protocol is one person model, and it's basically for via for for NSIGII vertical drift takeoff protocol via for drone delivery systems. Okay, so I'm trying to uh, uh, Okay, so you're gonna basically I'm trying to have a root a system take off vertically, but usually to have a area cover. So the area basically will be the what is it on the ground, and when it starts to have an area. So let me try to do it. Via codex line. So let me try to do it. So theorem, theorem A, theorem, drift theorem, drift theorem. Uh, uh, a drift is an angular shift, like redshift, uh, given a shift d, given shift a drift d is an angular shift given t uh, time minus okay, so, 1 minus t, 1 minus 1 minus t, a drift t given a drift t given time. Basically, a drift the angular shift d t given time 1 minus t given time is a projected point. It's a projection p, like a vector projection p in R3, in R3, in R3, such that, such that uh, 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 t, such that uh, minus tp minus pt d t such that p minus c such that t such that c minus such that uh, drift zero, drift is an angular shift, such in a position and is a position p, now such that p minus c, such that p, such as so basically a drift is an angular shift such that in given time t, uh, or time t, such that such that p, so that p uh, 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 um, so the p uh, p minus c p and c so that p so the p minus and c is the camera projection camera position in R3. So just so d t equals p t minus c t. The drift t, where t is double, is the magnitude of b squared minus 4ac uh, given interval p T is a vector projection of shadow uh, using position function, and C is a camera projection point. C is the camera position. So I do not work out verb progression, but out with space as well. So you get elliptic curve trajectory, and you get something in orbit, something not in orbit, something in orbit, something that's going out of it. So you're gonna have so if I have the first orbit, if I have T is a projecting spline, T is in change in or changing T is basically T is such that T is changing T. So that's one. So the drift is an angular shift. So basically, you can now try to model when thrust is gonna come in. But if you have something that's coming through, this model applies. And basically, the spring for this model. So this is what I'm saying. So this has come into equation. So drones can, if I basically 100 feet, 100 meters in the air, we'll have to start going up somewhere. So this is what I'm saying. It's gonna have to measure something. This is a drone carrying weight, and this weight will be some kilograms of weight, and goes in orbit. So let's find another video to do it. So let me try to find this. So this is 5 kgs carrying. Uh, let's say it's 100 kilograms, a bag of rice. 100 kilograms, a bag of rice. 100 kilograms. And the drone weighs. The drone is 200 kilograms. If the drone is carrying, basically the speed can fall at any time. So you have to slow down the speed up based on the what is observed. So get a minus cosine. So the model is that. So the first thing, so if I have a ruler, let me just use this guys. I'm Nigerian, like doesn't really mean anything to me. And you have a takeoff height. Drift of so basically, so you're gonna have two lines, two left lines. You're gonna have two left lines. You're gonna have D north or 390 degrees. The angular shift of 90. So, for example, let's apply this formula here. So, a drift of 90 degrees would be at time equal. So let's try to formula. I'm trying to get the problem down. So if I can't solve this problem, I failed it. I failed what I'm doing, guys. Because I gave myself this problem to solve. He was to solve it. The drift, the drone carrying 100 kilograms of 100 grams, 100, 1,000, 1,000, 1,000, 1 kg of rice takes up vertically, vertically, horizontally, vertically, uh, at 250, at 50 meters, at 50 meters, uh, uh, at 50 meters for every 10 seconds. Let's say Uh, 50 meters every 20 seconds. You know, calculate the drift of basically you have to know you have left and right drift. So calculate a drone carrying a liquid or bag of rice takes up takes off vertically at 50 meters for 20 seconds. 50 meters per second. 50 meters per second. You know, 50 meters, 50 meters per second. You know, that's kind of a very fast drone. You know, but you know, I don't think it's possible. You know, per second. I'm just getting started there. You know, basically, I'm trying to. No, we don't need trust. We don't need them. It's a drone delivery system. So, 50 meters per second will be a drone delivery carrying 1 kg. 1 kg. Let's just say 50 basically drone height is basically 50 meters per second. Determine when it is determining uh, uh, determine when at what time the drone will reach orbital velocity given a elliptical curve trajectory and B. Uh, the elliptical is basically the parabola. So it's a drone carrying 100 grams of rice, 100 gram, 100, should I make it 1,100? 100 grams, 100 grams of bag of rice. Let's make it 500 grams. 500 grams of bag of rice. Six vertically. Uh, uh, how many miles is flying? Okay, let's say per second, 50 miles per hour, per 50 meters, 50 minutes per hour, basically. I don't know, 150 meters per hour, 150 meters per hour. So you're gonna have the system work here. So I'll give yourself a question and solve this problem. And I don't really know what I'm gonna do to this problem, but I'm gonna try to have the system work. So you're gonna have minus sign, minus cosine. When you but let's try to do it. So you know, I'm gonna have to follow home. So let's try to do it. So a position point P is determined by geometry, two-thirds of geometry, and half dimension. Uh, so let me try to find how to do vector projection again. I forgot, I forgot how to do vector projection. So vector projection, use of units, base units, the derivative units, common user quantities. Seven base units. Yeah, limited by units first. 1000 grams. 1 kg, 1000 grams. 1 kg. So, I'm trying to find the video now for the system. But I'm gonna go message here for the Sparse so I'm not gonna use it, yeah, but it's gonna go up vertically, do a loop to loop, do a loop to curve and come down. So let me try to do so, so these are called stages. So, I could do this, but I'm gonna do well with it. So let me try and model what I was doing. For 2 minutes, so let me try and do it. I failed already because this video has to come back later. So, D given T is the training T is given by B squared minus 4C. So let's try to do it properly. Let's try to do this properly. Let's try to do this properly. Let's try to do this properly. Projection T is given 1 minus T, 2/3 C times plus 1/3 T, 2/3 C times 1/3 plus 1/3 uh, P. So the position doesn't really matter geometrically. So there's an area of land, there's an area on the curve. I'm looking like an area on the curve that dictates the projection point of the space here. So this is basically the space here. This is it. As it goes up, as the drone goes up, it has to lift the weight, and that leads is So the question is, let me try to give it to AI. So let me try to. The drone carries 1 kg of bag of rice. To get up vertically, 150 meters. 150. Let's say 20 meters divided by 1 second. 20. 50. 150 meters per. 150 meters. First of all, per second. That's uh, um. So this is no question. This is not physical question. So okay, 150 meters given can carry can at 15 meters for a drone carries 100 kg, 1000 kg at 15 meters for every 2 seconds. For every let's say 15 meters. Basically, the formula here, the triangular formula here, v equals of velocity equals distance over time. So this over time. So v equals distance c. Velocity equals distance over time. So that's why I was stuck. And I'll go for 5 minutes now. Can I go? So let me try to do this properly. So after pause this video and stop it now. So basically, I'm going to take this formula, velocity equals distance over time, and apply it to the drift theorem and the potential for the equation. This is to plug into b squared minus 4c. So there's no zero, zero interval. It doesn't reach a zero interval, but that's the video done. This is done. This is the next video.